Bismillah ar-Rahman ar-Rahim. So last time we talked about the roles of the transport layer. We talked about tracking conversation. We talked about segmentation and reassembly. And we need to try to relate things together. So we talked about, so segmentation is about dividing the information into segments, right? Similarly, we have done this in the network layer. Do you remember we called it a fragmentation, right? So fragmentation is also about dividing the message or the segment into smaller packets, right? But the purpose was different. Segmentation is done to facilitate multiplexing of the conversation, right? To facilitate sharing the network resources amongst multiple conversations or multiple applications, right? Fragmentation, the purpose for it was different. Do you remember? The purpose for fragmentation was the fact that when we move from one network to another, the network medium might change, and there is more limitations and stuff, and that's why we have to track the network medium, and we have to do some fragmentation and reassembly and stuff. But the purpose was different. The purpose was to accommodate the limitation of the medium rather than facilitating the multiplexing of conversations. So, and then we call this segmentation, we call this fragmentation. So the terminology also distinguishes which layer we talk about. So today we want to talk about the most common two transport layer protocols, TCP and UDP. Some of you have already done some programming even using these protocols, so you have some idea about them. TCP and UDP provide two extremes, two like very distinguished extremes of protocols in the transport layer. TCP gives you everything, and UDP does not give you anything, in brief. So TCP is a connection-oriented protocol. It has to establish a connection end-to-end between the two applications before you communicate. Hence, it provides guarantees on the order delivery. It requires some reliability. And it provides flow control and congestion control. Reliability is done through, again, response time out. So when I send a segment, I expect the receiving node to send me back an acknowledgement. If I don't get that within a timeout, then I do retransmission, right? Flow control talks about controlling the speed of the transmission so that I do not overwhelm the receiving node. We talked about all these concepts, if you remember, in chapter even 3, right? So TCP provides all of this. Flow control, reliability, congestion control, order delivery, everything, okay? But the problem is that TCP gives you the whole thing. It's one package, take it or leave it. You cannot just say, I want to use TCP, but I don't want flow control. You can't. This is how TCP works. Take it or leave it, right? So in some applications that we talked about, TCP is not good at all. Like what? Do you remember?
DNS could be a speed.
Huh?
For speed, like fast applications.
Yeah.
Fast applications. Like what?
Low delay.
Application that don't need it.
Ping video.
Video, bravo عليك. How video? Yeah, video streaming is one of the very obvious applications that they require speed. They require real time. Okay, like VoIP, IPTV, video streaming, like through Google and stuff, through YouTube. يعني. So these applications, they cannot afford retransmission of segments over and over again because this will cause some pauses in the video. On the other side, these applications can really tolerate some segment loss because segment loss will result in like some few pixels on the screen. Well, the eye tends to have averaging of the whole scene, so your eye will not even notice if there is any one pixel or few pixels lost from each frame. It actually auto-corrects that. So you will not notice this unless there is a pause in the video. This actually causes terrible experience for the user, right? Because it's very noticeable. So delay is really critical for this application, especially streaming applications. But segment loss is okay. It's fine as long as, of course, it's not like 25% or 50%. And which is the case. So that's why TCP, even though it has all these good things, flow control, reliability, connection, and everything, in many applications it's not attractive, and it's not as fast as these applications would require. And that's why UDP, even though it does not provide anything, it's baseline, does not establish a connection, does not guarantee order delivery, does not provide any reliability, does not provide any flow control, it does not control the speed. If you actually, if you put too many segments in the buffer of the UDP socket, the transmission will be, these segments will be back to back like this, will be sent back to back like this, with no time in between, which might cause serious problems. Sometimes they overwhelm the receiving node, and sometimes they even congest the network. Congesting the network, we call it congestion control. So congestion control and flow control, they talk about controlling the speed of transmission. TCP does that, UDP doesn't. So flow control talks about controlling the speed with the purpose of not overwhelming the user or the receiving node. Congestion control talks about controlling the speed with the purpose of not jamming the network or not congesting the network. See, it's a slight difference. But both of them, they talk about controlling speed. Okay, both of them, they talk about controlling speed. In some cases, some senior project students, they came and talked to me about, not having communication, and the communication seems to be lost, and sometimes they have communication between two nodes and one node goes down and stuff. And in analyzing the problem, sometimes you use UDP and you don't provide any flow control. So you overwhelm the receiving node, and the receiving node tends to go down. They actually use the same concept for DDoS attacks. If some of you know about the DDoS attack, denial of service attack for security, they send back-to-back segments to the servers to bring them down. And they have no delay in between. And these requests are legitimate. And they try to pretend that they use different source address and stuff to give the server the problem that, these are different users, even though it's the same user. There is a very interesting link, I may actually post it. It shows you the map of the world and all the DDoS attacks that happen from one country to another. So DDoS attack is based on this concept. It's based on sending back-to-back segments to overwhelm the receiving node. Okay? So TCP, it does flow control, and we'll see how TCP performs this controlling of the speed and how it works. Okay. So very quickly, we need to write here in the box. We need to write some words. Okay, it's not just tick, because in some cases, like tracking conversations, as we said last time, both of them they track conversations, right? Both of them they provide separate flows and separate conversations. Okay. So we'll try to write here some words that will distinguish these two protocols from each other as an initial comparison. And later on, we will compare them more deeply. Okay? So for tracking conversations, as we said, both of them, they track conversations, right? They provide individual conversations. But if I were to distinguish between them, TCP does that through connections, right? It's through connection establishment.
So it's not tick?
Tick. Okay, and this one is tick, but this one is connectionless. Okay, this one is connectionless. It does not establish a connection. Establishing the connection is part of the delay, by the way, because I have to wait for the connection to get established before I send back and forth any segments. And that requires, it adds to the delay, right? Acknowledgement segments is just, there's no doubt about this. This one provides, this one doesn't. Okay? Retransmitting, also this one provides, this one doesn't. Okay? Speed, which one? So this one provides low speed or lower. This one is higher speed. Okay, which is actually one of the factors that some applications they use UDP. Segment overhead. This one actually has high segment overhead. This one has low, very low segment overhead.
دكتور ليش
السيجمنت overhead اللي هو the header that gets added to the segment itself. TCP, because TCP provides flow control, congestion control, and all of this, it requires more fields, as we will see on Sunday, inshallah. It requires more and more fields, so the segment tends to be larger for TCP. But there is no way around it, because we need flow control, we need reliability, so we need acknowledgement, we need to track the acknowledgement number and the sequence number and so on and so forth. This adds to the segment overhead.
What do we call sending the segments back to back?
Well, we call them back to back. There's no inter-segment transmission time. So sometimes the UDP, because UDP does not provide any flow control, in some cases it happened to some students, as I said, and it happened to us even while we are implementing some protocols for research and things like that. If you don't pay attention to this, sometimes you cause what we call back pressure. So you send to a node, like for example sensors send to a cell phone, and this cell phone sends to the server. This scenario is very common in IoT, right? So we do it a lot in our research. So the sensors send these segments to the cell phone using UDP, because we don't need, for short range communication, we don't need the overhead of TCP. So sometimes we use UDP. The problem with that is that the signals arrive very fast to the cell phone, but the cell phone talks like 4G, or it uses Wi-Fi or something like this to send to the server. So if the buffer of the cell phone does not get emptied, the segments will arrive back to back and they will overwhelm the buffer of the cell phone. And sometimes we have the problem of no communication is happening and we don't know what's going on. So the problem is back pressure on the cell phone. The cell phone is actually receiving these segments back to back. The buffer gets filled very quickly, and there is buffer overflow. And if there is any buffer overflow, sometimes for some protocols, they close the connection completely. In these applications, you can actually, what you could do is that you can use UDP. UDP gives you baseline, right? And from the application, you can just send one segment, wait for some time, okay? Let's say like 50 milliseconds or something, and then send the other segment. Surprisingly, this works like a magic in some scenarios, and we tried that. This is the easiest way of providing flow control. But of course, that's not how TCP works. We'll see how TCP controls the speed. It's not like this. This is the easiest way. And this number can increase or decrease, but it's manual. Okay, so you do it arbitrarily. But the flow control is a lot more than that. Okay, but even this works in many scenarios. Anyway, so in terms of applications, any application layer protocol that uses file transfer or uses frequent messages that provides any kind of reliability, like HTTP, like FTP, like Telnet, all of them, of course, they use a TCP. So here, HTTP, FTP, Telnet, all of these application layer protocols, they use TCP. بوضوح, صح? They require some kind of reliability. Any application that deals with video or audio, it's audio streaming, like IPTV, like VoIP, they use UDP. Some protocols, they require very lightweight messages, and they do not require any reliability, especially if these messages are broadcast messages, like DHCP, for example. DHCP uses UDP because the messages are not meant to be very frequent messages, or they are not like for file transfer, and they are sent as broadcast. TCP is very bad for broadcast messages. Why? Because if you send any message as broadcast, you require acknowledgement from the receiver. Well, the receiver in that case is all nodes. So if you wait for all nodes to send you back acknowledgement, good luck, because you will wait forever. So it's very bad in doing this. TCP is very bad for protocols based on broadcast messages. And some applications, application layer protocol that require combined messages, like broadcast messages and non-broadcast messages, like replies and stuff like that, both of them can be used. And that's possible in the case of DNS. So DNS can use either, or it can use both combined actually. DNS, okay? Okay, so this is actually briefed or actually detailed in this columns here. So both, as we said, DNS tends to use both. This is the only protocol that tends to use both of them. TCP, so we want to talk about applications that use TCP and UDP. So very quickly, any applications that use video or streaming or something like that clearly use UDP. Any applications that use other than that, like file transfer and things like this, they clearly use TCP. And there are some applications that will be like gray level. So we'll talk about these. Okay. So this is the categorization of the different applications and what protocol they use. Okay. Simple messaging transfer protocol. This is for email. We'll talk about this in chapter 10 in details. Okay. Most of these protocols we'll talk about in chapter 10, but some of them we'll just ignore, like VoIP and IPTV we'll not talk about.